Hello friends, this is Jim here, Science Talk, and in this video presentation I want to discuss with you polar ice, sea ice specifically. And I'm going to cover both what's going on in the Arctic and what's going on around Antarctic. So first let's start here with the Arctic. And as you can see here in this graph, Arctic sea ice extent over the last 1,500 years. And what do we have on the vertical axis? We have the Arctic sea ice extent that's given in millions of square kilometers. So from 8 to 12 billion square kilometers. And this is basically going back from 600 AD or current epoch all the way up to 2000. Now, if you look at this, you can see that there's sort of a cyclical pattern here for most of the record that goes back 1,500 years. A little bit of an increase. We see a maximum in about, late 1400s. Here's 1500s. This is late 1400s. What was happening in the late 1400s? A thing called the Little Ice Age. And we can actually see this here in the information. Now, when are they getting, how are they creating this plot? And first of all, this is courtesy of NOAA, climate.gov, and the data is from Kinhard et al., Kinnard et al., 2011. So basically, what they've done is they've looked at the ice cores. They're able to reconstruct past climate situations by looking at the ice cores, measuring the CO2 concentrations in the trapped gas bubble. They look at the oxygen 18, oxygen 16 ratio, the Del 18O. And from there, they can ascertain what the ice is doing. Now, the cyclical nature, of course, reflects seasonal changes. So, as we see here, we have the little ice age, then it starts cooling down, and levels drop, build back up. But then look what's happening here. It dives off. This is remarkably quick. So if this is 1900, in about less than 100 years or so, it went from, on average, say about 10.3 square kilometers to 8.3 square kilometers approximately. So a loss of nearly 2 million square kilometers. Remember, this is millions of kilometers. So 10.3 million square kilometers to 8.3 million square kilometers. Major, major drop off. Now, this past week in Fairbanks, we've had snow. And it snowed just about every bloody day. Why is that? Well, you could say, well, it's just a little quirky weather variation. That can happen. We've had snow before in April, May, even on solstice. But the snow events we've had in the past was like an inch at most, and it quickly melted because of the fact we have more daylight, things are melting faster, etc. This snow event was, at least where at my home, was 4 to 5 inches of the wet, heavy stuff. The Arctic Ocean extent, as we've seen here, and I got a couple more graphs to show you, is not as extensive. The ice is not as thick. There's more open water. Open water, not as thick ice, leads to more moisture in the air, especially with warmer air atmospheric temperatures, holding more moisture. You get the appropriate wind pattern, jet stream pattern, brings down that moisture laden air, and we have a wee bit of a dumpage. And that's basically what's going on. We're seeing more of that, by the way. So let's this is very dramatic here. Boom, it just drops right off, almost tanks. Now, oceanographers usually define open or ice-free Arctic as containing less than 1 million square kilometers of ice. And we're getting there. Let's take a look at the next slide here. Okay, Northern Hemisphere sea ice extent, August anomalies from 1979 to 2018. So this is basically pretty much a 40-year record of what's going on. Now, the zero line here is the average. So anything above is a positive anomaly, anything below is a negative anomaly. The extent anomaly is in percent. Okay, so this is percent. So we can go all the way up to, the scale goes up to 14. The highest value you see is about here, and here is about 13%, meaning 13% more ice coverage than the average. And it goes all the way down to negative 36 on the scale, and the years from here's 1979, 2018. What do we notice here? Starting at about the year 2001, 2002, all negative, meaning that the sea ice extent for basically this entire 21st century is less than average. That's what this graph is showing us. It got really low in 2012. That also correlates with an El Nino event, and I am preparing videos on El Nino, ENSO, the PDO, the IPO, the NAO, the AO. So it's just taking some time to put it together. But I am preparing that, so look for basically a series of videos coming sometime soon. So this just shows, even here, this is a La Nina event. Even with La Nina, the sea ice extent is less than what it should be, than what the historical average is. This is also a very telling graph, which correlates to this graph, where we just see things tank out. Now, of course, this has a bigger scale, so you're not going to see the fine details like from here to here as this graph shows, but nevertheless, we see a tanking in the extent of the Arctic sea ice. Now, if you look here, it says 1981 to 2010 average is 7.2 million square kilometers. The trend is a decline of 10.4% per decade. That is not insignificant. Not at all. And this data comes from the NSIDC, National Snow and Ice Data Center. They're located in Boulder, Colorado. So these folks, this is what they do. One of many things. Anything to do with the cryosphere, you can rest assured these guys are in on it. It's a good organization. And of course, in collaboration with NOAA. So now let's look at the Arctic sea ice volume anomaly. Now this is volume. The previous two slides that I shared with you show the extent. So we're measuring things in square millions of kilometers. Now it's an area. Now the volume takes into account the thickness of the ice. Now what do we have here? Ice volume anomaly relative to 1979 to 2017. 1,000 kilometers there. And then we started from 1980 all the way up to, well, actually 79, right, on that, all the way up to 2019. And the last day is May 31st of 2018. The anomaly trend, minus 3.1 plus or minus 1.0 thousand cubic kilometers per decade. So this is based on 1,000 cubic kilometers. The trend, minus 3.1, that's the average, plus or minus 1. And this is, of course, going to be in 1,000 cubic kilometers per decade. Plus or minus 1 is your error, standard deviation. So we have all these measurements here. And then this blue line right in the middle is the fitted regression line. And what are these shaded? We have a light shaded area here, and then even a lighter shaded area here. So it's a little darker here. And what do we have here? Well, here's the description of the figure that I just showed, and I'll pull it back up. Arctic sea ice volume anomaly from PIOMAS. Okay, PIOMAS is Pan-Arctic Ice Ocean Modeling and Assimilation System. That's PIOMAS. Okay, updated once a month. Daily sea ice volume anomalies for each day are computed relative to the 79th of 2018 average for that day of the year. So they're looking at what the average ice is on that day, all 365 days. Tick marks on the time axis refer to the first day of the year. Okay, let's go back up and look at that. The tick marks. So when we look, I'm pulling 1990 as an example. This tick right here, that is January 1st, all the way to December 31st, and then that is January 1st, 1991, all the way until we get to January 1st, 1992, etc. Okay. The trend for the period 79 to present is shown in blue. Shaded areas show 1 and 2 standard deviations from the trend. Error bars indicate the uncertainty of the monthly anomaly plotted once per year for that day. All right, let's look. So this from here to here is 1 standard deviation around the mean. From here to here is 2 standard deviations around the mean. Now, in statistical theory, and you may recall that I presented some videos on introductory statistics. So if you haven't seen those, please check those out. But basically, when we look at the typical bell curve, the so-called normal curve, the mean is at the top. And then if you go 1 standard deviation below the mean to 1 standard deviation above the mean, that accounts for 68% of the data. If you go from 2 standard deviations below to 2 standard deviations above, that accounts for 95% of the data. And then plus or minus 3 is 99.7% of the data, nearly everything. So as you can see here, this is accounting for 95% of the data, and this little bit is falling outside 2 standard deviations below, the same thing here. So this does account for most of the data. This line with the negative slope is what this is, the minus 3.1 plus or minus the 1. So we see a clear trend in the volume of ice decreasing as well. We've already talked about how the surface area is decreasing. The volume of the ice is decreasing. And this is backed up by observations and measurements that indicate the prevalence and the occurrence of multi-year ice is decreasing. Multi-year ice is how you get the really thick stuff. Now we're getting 1-year-old ice, 2-year-old ice, some 3-year-old ice, but 4, 5, 6-year-old ice is not as frequent. So this is another telling graph showing how the Arctic ice is decreasing in volume, is decreasing in extent. So that's, if you want, you can pause the video here and grab a hold of this website if you wish to look at the work they have published. So what's the take-home message from all of this? Well, let's see. Remember I did a little thing about the Bering Sea ice. Well, okay, here's some actual data. The last time I talked about the Bering Sea ice was kind of based on the observations of Dr. Rick Toman. And here we have some data now that shows what's going on. And again, this is from the NSIDC, right? You know, anywhere there's ice, you got to find these guys. And if you hear that sound in the background, it's my dog insisting on drinking all the water in her water bowl. So you hear that kind of strange sound in the background. So she's old, so let her be. 13-year-old Malamute. The average lifespan is 10 to 12 years. So you still with me? You good girl. All right. So you see, we're starting from 79. Again, this is going up to probably just about to 2019 or so. They're doing in 5-year increments here on the horizontal scale. And what we're seeing is basically, the extent of how much ice is in the Bering Sea. Again, this would be in the square, in this case, tens of thousands of square kilometers. Got down low here in about 2002, 2003, which correlates to, overshot this guy here, right? And then see some peaks here. This is, this is winter time. This is summertime when it melts back. But now look what's happening over the last basically 6, 7 years or so. It's dropping. So the ice is diminishing in the Arctic, both in terms of the area covered and in the volume. Okay, now we're going to go switch our attention, excuse me, to the other side of the planet. And this is a model showing the situation of what goes on in Antarctica. So we have the ice sheet here. So this is land ice. This is a mountain poking through Nunavut. Now, you see this dashed line here. This dashed line is right on the grounding line. This darker coloration here represents, the surface, the continent, if you will, along with a little bit of a continental shelf, and then again into the continental slope. This is the bedrock. The grounding line is the line where the ice rests on the bedrock. Beyond the grounding line, the ice is not resting on the bedrock. And that's, you can see this little space here, that corresponds to the floating ice shelf. So when you get from here this way, this ice is floating. Some of it will break off and you get an iceberg. Nice little chunk of ice there, and so on. Ocean currents flow under the ice. If the ocean currents are warming, and they are, then you're going to get some melting from below. What does that do to the ice? It weakens it. And if it weakens, it's going to more likely break off, which is indicated by these little pieces here. Okay. Now, this is land ice. This is not including the sea ice in the model. This is just what's happening to land ice. Remember, I have done videos before in the past where the sea ice helps hold back the land ice. Well, the sea ice is also disappearing or reduced in volume and extent in Antarctica, so there's not much resistance holding back the land ice, so it's going to slowly move or increase its rate. It goes slowly, but it's going to increase its rate. Then you're going to have unsupported ice over the ocean, gets warm from below, and it starts breaking off. Eventually, currents carry the icebergs into warmer water where it melts, contributes to sea level rises. So this is another model that goes into a little more detail as to what's taking place. So here's the Antarctic ice sheet. We got snow coming down. It's going to accumulate. Very nice. Here's the ice shelf. Here's the grounding line again. So now you see how the ice this way is resting on bedrock. The ice from this point this way is not. So we got some basal melt refreezing, basal crevices, surface, crevasses. And then the flow of the glacier, obviously this way. There's a satellite overhead, taking all the nice measurements. We've got icebergs breaking off. Here's the sea ice. Now, let's look at what's happening here. So here's the continental shelf. This represents the continental slope. And the CDW, I don't know if you can see that, but these letters here, CDW, means cold, dense water. It sinks, right? Remember, density of seawater is determined by temperature and salinity. Cold, dense water is the densest possibility that you have. So this is going to be at the bottom, which is not to be unexpected. We expect that. So what do we have? We have high salinity shelf water that gets in underneath. We have some mixing going on, tidal mixing, just the basic physical processes and so on. Now, some of the cold, dense water through what can be called onshore Ekman transport. I'm not going to get into that. That's a very involved physical processing, but it's a one-way to get water, cold, dense water, onto the shelf, which is what this is representing. So this is cold, dense water here, all the way to here. This is intermediate dense water here. You get some of the mixing here, that's high salinity mixing. So if you have high salinity shelf water mixing with cold, dense water, there's going to be some turbulence. Now, this tidal mixing is from tide action. So there's going to be some turbulence. Due to local actions taking place, there's going to be some melting. There's going to be some brine rejection, maybe some melting of the water itself to add a little bit of fresh water, decrease the salinity a bit, decrease the density a bit. Or you can have some of the crevasses where there's infiltrations into the ice. The bottom of the ice is not a smooth thing. It is bumpy, it is full of ridges, it is full of holes, it is full of, well, it's just not smooth. Let's put it that way. So you're going to get some infiltration. So these are going to be local events, local phenomenon taking place, but when you add them up, it can lead to a destabilization of the ice shelf. So from the mixing and the general physics of temperature and salt, you're going to have some cracks forming in the ice. If you start warming up the water, you're going to have some warm water currents flowing in there. That could lead to some melting underneath. And then you get these little crevasses infiltrating. Sometimes they might refreeze, but don't forget, if they refreeze, there might be a little bit of expansion. And the refreezing will reject the brine, so making the water dense again. So you could have some freshwater input to decrease the salinity, some refreezing, which puts brine back in there, increasing the salinity. It's very turbulent, is what I'm trying to say here. Very turbulent processes going on here. And with all this turbulence from what's going on with the ice, from what's going on with the water, will weaken, especially with increasing surface water temperature, get some flow underneath there. It will weaken the ice shelf, and you start splitting these off and get these icebergs. Sea ice starts melting. There's nothing going to be holding the ice shelf as back. So this is kind of just a little diagram to kind of give you a hint of some of the processes going on in the ice and how these processes can lead to the significant chunks of the ice shelf just breaking off. So now, this slide here, and by the way, it's just a diagram I found. This slide here, our old friend, NSIDC, University of Colorado Boulder, this is now showing not the land ice, but this is showing the sea ice. This is all sea ice. So, this yellow-orange line here, whatever. But this yellowish-orangey line here is the median ice edge from 1981 to 2010. So that's the median ice edge all around the continent. Okay. These little dots here, they say missing here. That's just some missing data, probably blind spots in the satellite, what have you. So there's a couple of missing data, either for ice or ocean temperature, what have you, but it's not critical to what I wish to illustrate here. So here's South America. So this is Drake's Passage. Some nasty waters here. Okay, if you were to go cruising at this, let's see, this is 90, so that's 85, 80, 75, 70. So this is about 65 degrees south latitude. You will note if you stay on 65 degrees south latitude, you will not hit any land. And so, not surprisingly, we have the circumpolar Antarctic current. They go rip-roaring around Antarctica. Makes for some of the nastiest waters on the planet. So, what do we have here? Let's now look at this scale here. This scale here is basically 0% means open water. This is open water. Open water, open water, open water. As we go further up the scale, we notice it starts turning to a turquoise, then blue color, light and lighter blue, very light blue, till we get to almost white. Almost white is basically pretty much solid ice, where you're going to have the highest albedo, the highest reflectance of sun energy back into space. Don't forget, this is still covered with ice, land ice. This is just looking at sea ice. So this sea ice is not as thick as that sea ice. So this is going to be more multi-year ice. More multi-year ice. Not so much multi-year ice. But look at this. This is the median extent. Look how much more open ocean there is now. So if you have less, there's nothing, practically nothing here. There's nothing to prevent land ice from going bloop, right off that way. More likely to go galloping off the continent this way, and here, and here. This is a dramatic decrease in sea ice area. Dramatic decrease. Now, I want to show you this photo. This is from the Canadian Arctic archipelago. This is a photo probably taken in the late 1940s, something like that. You can see it's a big, huge wall of ice. You can see a couple peaks poking through. Same place. Taken a few years ago. Here are those peaks. Right? Yeah, 1, 2, 3. 1, 2, 3. The ice is, for all intents and purposes, gone. This is a pretty damn dramatic comparison of photos. Let's let that sink in for a bit. One for these peaks poking up, they wouldn't know there was land back there. Now look at it. And even though it has nothing to do with ice, I couldn't help myself because I am tired of people saying, well, you scientists can't agree on anything and it's all made up BS and yada, yada, yada. And you guys are, and I'll be honest, this is what really pisses me off, is when I hear people saying, well, you guys are just writing the stuff just to scare us or just to keep your funding. First of all, when you say we're writing stuff to scare people, that's accusing us of intellectual dishonesty. That's actually libelous. We're not writing anything that we, if you find it scary, then you know what? The information we're presenting is alarming. And you should bloody pay attention to it. And to say we're doing it to keep the grant money in. We wanted the grant money. We go work for the oil companies, to spew their propaganda and make about 7 times the amount of money. So please, I'm sick of hearing that. And you mean to say that scientists from all over the planet and publishing papers in all the journals are in a conspiracy? Give me a break. Okay. So some scientists can't agree on Earth's temperature changes. Here's what this agreement looks like. Okay, let's look at this graph here. Temperature anomalies. Again, the 0 is the basal average. So above the line is higher than average. Below is cooler than average. Now, let's look at the sources here. This, I guess you call that a magenta line. This is from NASA Goddard Institute for Space Studies. This is the agency that Dr. Jim Hansen was at. Then we have the Met Office Hadley Center Climatic Research Unit. This is a research unit out of the UK. That's in blue. Then we have NOAA. National Climatic Data Center, National Oceanic Atmospheric Administration. So that is in this, I guess, yellowish, greenish color. Then we have the Japanese Meteorological Agency in purple. So we've got the US, Japan, and the UK presenting the data. And yes, there are going to be some differences, slight differences here. You know, probably the biggest departures are maybe here and here. And here, in fact, it looks like the Japanese scientists have a tendency to record on the lower end of things, but the overall trend is unmistakable. Right? Fit the line right there. Okay, here's 1960, here's 1980, and bang. From 1980 on, well, actually more, yeah, 1980 on, yeah, all the anomalies are above average. The planet is warming. And when you look at this, okay, this is, it's now reaching about basically half a degree C, the anomaly. Average temperature takes into account where it got cooler. Okay? But if you really wanted to look at from, this doesn't go back far enough, but from -5 to +5, that's your 1 degree that you keep hearing and spoke about in the press clippings and so on. So yeah, if this is what disagreement looks like, what does agreement look like, right? Yeah. Scientists, our data, we have our ways of doing things, collecting the data, tried and proven methodology, and we're basically reinforcing what we are finding. These are all done independently, and then we compare our notes and say, oh, okay, yeah, we're getting that too. Okay, yeah, right? This is what's going on. So I just wanted to throw that in. But going back to here, we see the sea ice decreasing. And we know about the chunks of, from Larsen B shelf, we know about the chunks of land ice breaking off. There's some models showing it's going on. We see the Bering Sea ice is decreasing. We see that the volume of ice is decreasing. We see that the extent, the square area covered, is decreasing. And this is all happening within a matter of decades. This is not what we see as a natural cycle. This is not natural forcing. This is human forcing. That's plain and simple. The time scale is so short that is much shorter than any natural forcing cycle. This is obviously human forcing cycle. I wanted to bring this to you. Hope you found this informative, and thank you for your time. Hey friends, this is Jim reminding you to subscribe and share my videos. Also, don't forget to click the bell so that you know when I drop a video in. And I'm also asking for you to please support the work that I do by becoming a patron at patreon.com. Details in the description box below. Thank you for your continued support.